Okay, so this is still section 3.1. And it's the last half of it. And it's on domain and range. And domain and range are concepts that are related only to functions and not relations. And we can define the domain of a relation of a function. The domain of a function, or when y is a function of x, is all the x coordinates of the points that make up the function. And the range of a function would be all the y coordinates. So the domain is all the x coordinates of all the points that make up a function. The range of a function would be all the y coordinates of the points that make up the function. So ranges are y coordinates. Domains are x coordinates. Unfortunately, in the world of functions, just like in the world of relations, we have finite functions and we have infinite functions. A finite function is a function that only has a fixed number of points, like each of the problems 27, 28, 29, and 30 are finite functions. So a finite function has a countable number of points. And the domain of a finite function is found by listing each x coordinate of every point inside set braces. The range of a finite function is found by listing each y coordinate of every point and placing him inside set braces, which are these little curly braces. So if a function is a finite function, I'm going to use set braces to list the domain and list the range. Problems 27, 28, 29, and 30 are relations that are defined as sets as points, and each one of these problems, 27, 28, 29, and 30, are finite relations. 27 has 3 points, 28 has 4 points, 29 has 5 points, 30 has 2 points. Each one of these are considered finite relations because I can count the number of points. If I could count the number of points, I'm going to list the domain of the function by listing each of the x coordinates and putting them inside set braces, and I'm going to find the range by listing all the y coordinates and putting them inside set braces. So the instructions for problems 27 and 45 say determine the domain and range of each function, and then it says write your answer in interval notation where appropriate. That's a little premature, and once we get to infinite relations, this is going to be appropriate, and I'll talk about that in a second. But for 27, 28, 29, and 30, these are finite relations. I write the domain of a finite relation by creating curly brackets, or set braces, and I write the range of a finite relation by creating curly braces. For the domain, I write the x coordinates of each of the points. So if I was doing 27, I'd say the domain is 1, 3, and 5, which is just the 3 points x coordinates. And I would say the range is 2, 4, and 6, each of the points y coordinates. When you're using set braces to explain the domain and the range of a function, it's not necessary to write the numbers in ascending or descending order, and it's not necessary to write a number if it comes up more than once. When I go to do 28, for 28, because it's a finite relation, I'm going to say the domain. Now I'm going to write set braces, and I'm going to write the x coordinates of 3, 5, 9, and 8. It might be better for problem 28 if I said the domain, I'll just write D for domain, is 3, 5, 8, and 9, writing the numbers in ascending order, but it's not wrong. When you have finite functions, writing the domain is just the x coordinates of each of the points, and they can be in set braces, but they don't have to be in set braces. When I go to do number 28, the range, I could go, the y's are 2, 7, 1, and 1. Numbers aren't in ascending order, and I've duplicated some numbers. That's probably not the best answer. It would be better if I didn't write 2 1s and I wrote the numbers in ascending order and wrote 1, 2, and 7 for my range. But both of these are correct ranges, just like both of these are correct domains. For finite relations, domain and range are just the listing of x and y coordinates. For my problem 30, my domain is going to be the points 0 and -1. They're written in descending order. I can live with that. And my range is going to contain the points 3 and 5. So you should be able to do, I guess I just left you with problem 29. I'm going to flip on to the next page. The next page gives me a function that's defined graphically, but it's still a finite relation because it only has a finite number of points. So problems 31 and 32, problem 31, the function is a finite function, in number 31, we could say f for function has the points 112, -50, and -3, -4. Because it's possible to list all the points, that's considered a finite function. The domain is going to be the list of all the x coordinates. The range is going to be the list of all the y coordinates. Ooh, problem 32 is not a function because it has duplicate x's. That's maybe not the best example because it's not a function. Let me take this point away from problem 32 because to be a function, all your x's have to be different, and that had duplicate x's. It wasn't a function, so I'll go out and delete that so it's not there anymore. But nevertheless, I can find the domain and the range of this real easily. finite functions are the easiest kinds of functions to find the domain and range of. To find the domain of a finite function, I list the x coordinates of each of the points, in this case -3, 1, and 3. And to find the range, inside set braces, I write the y coordinates of each of the points, -2, 2, and 4. So if the points in a graph aren't connected and you're asked to find the domain and the range, it is very wrong to connect the points. You shouldn't connect the points, so do not connect the points in a finite relation. When attempting to find the domain and range. It's absolutely wrong. Lots of students just feel the urge to connect the points with some sort of shape, but that's not. If I wanted them to be connected, they'd be connected. And when the points that are listed are connected, the relation is no longer a finite relation, it's an infinite relation, and finding the domain in the range is different for infinite relations than finite relations. So the rest of the problems, 33 through 41, are going to be infinite relations because there's infinitely many points that are drawn, but they can't all be listed. So when the points on a graph are connected, the function, or the relation, function is a special type of relation, the function is considered an infinite function as opposed to a finite function. And when we have infinite functions, it's impossible to list every single x coordinate because there's infinitely many points. It's impossible to list every single y coordinate because there's infinitely many points. Because it is impossible to list all the x and the y values because there's infinitely many of them, we use interval notation to describe the domain and range. So the rest of the problems that we're going to do, 32 through 41, are going to be graphs where the points are connected. A few points will be labeled, but not all the points because there's infinitely many points. When the points are connected, it's called an infinite function. When a function has infinitely many points, it's impossible to list all the x and y, so we have to use interval notation to describe the domain and the range. And the domain, usually, it gets more complicated than this, but I have it written here, so I have to write it up. So for these problems, 32 through 41, the graphs have an infinite number of points. They're infinite functions. When it's impossible to list all the points, so the domain and the range need to be written in interval notation. And generally, for the domain, we write the x-coordinate of the far left point, followed by the x-coordinate of the far right point. And we put those inside, instead of square brackets, instead of squiggly brackets, we put it inside square brackets. Sometimes the square bracket will turn to a round bracket. I'll talk about that when it's appropriate. And for the range, we write the y-coordinate of the bottom point, followed by the y-coordinate of the top point. So What I'm going to do real quickly for this problem 32 is I'm going to start writing y coordinates on the y-axis, x coordinates on the x-axis. So this point 0, 10, I'm going to write a 0 on the x-axis and a 10 on the y-axis. For this point 3, 1, I'm going to write a 3 on the x-axis and a 1 on the y-axis. And for this point 5, 5, I'm going to write a 5 on the x-axis and a 5 on the y-axis. When I write my numbers of the points that are written like this, it's going to be maybe easier to see the domain and the range. The domain is the x coordinate of the far left edge of the graph, followed by the far right edge's x coordinate. Now if I look at my numbers on my x-axis, I threw 3 numbers on my x-axis. The first number that I wrote is the this is on the x-axis, not on the y-axis. The first number that I wrote is going to be the start of the domain. So for this function right here, the domain is going to start at x equal to 0, and it's going to end at x equal to 5. My domain goes from the x coordinate of the far left point, which is at point 0, 10. It's going to end at the x coordinate of the far right point, which is 5, 5. This point 3, 1, it's not the left edge, it's not the right edge. I'm not going to include that point 3 when I go to write my domain. For my range, I glance across the y-axis. The numbers that I wrote on the y-axis represent the y-coordinates of all the points that are written. For the range, I read from bottom to top. The bottom point is the point 3, 1. Its y-coordinate is 1. I'm going to start my range off with the number 1. The top point is the point 0, 10. I'm going to end my range off at 10. So if I take the points that are given to me, write their y-coordinates on the y-axis, write their x-coordinates on the x-axis, then the first y-coordinate is the start of the range, the last y-coordinate is the end of the range, the first x-coordinate is the start of the domain, the last x-coordinate is the end of the domain. Let me try to emphasize how I would do that with problem 33. So for problem 33, I would take the number -5, put it on my x-axis, -3, put it on my x-axis, and +1, mark it on my x-axis. So these are the x-coordinates of the 3 points. When I look at the x-coordinates of the 3 points, the domain is going to be the x, the first x, and then the last x. So for this problem right here, I would say the domain goes from x equal to -5 to x equal to 1. It's the x-coordinate of the far left point to the x-coordinate of the far right point. Now on my y-axis, I'm going to take the y-coordinates of the points. That point has a y-coordinate of -4. I'm going to write it on my y-axis. This point has a y-coordinate of 0. I'll write it on my y-axis. This point has a y-coordinate of 12. I'll write it on my y-axis. I'll look at the numbers that are the y-coordinates of the points, and for the range, I write the y-coordinate of the bottom point, which is going to be the lowest number on my y-axis, followed by the y-coordinate of the top point, which is going to be the last number on my y-axis. So the range for this graph is going to be -4, 12. The 0 that's in between those points isn't going to be included in the domain, but it's implied. This says in the range. This says the range is any number between y equal to -4 and y equal to 12. Because 0 is in between -4 and 12, 0 is assumed to be in there but not written. So for every single finite relation, I'm going to have to figure out the left edge and the right edge for the domain, the bottom and the top for the range. For problem 34, I'm going to start off, I'll take this point, its x-coordinate is -1. This point, its x-coordinate is 3. This point, its x-coordinate is 2. The domain, I read from left to right. The far left edge of this graph has an x-coordinate of -1. The far right edge of this graph has an x-coordinate of 2. So my domain is going to be -1 to 2. Now I'm going to do the same thing but with the y's. This point right here has a y of -2. This point right here has a y of 0. This point right here has a y of 4. So I'm looking at the numbers -2, 0, and 4. I read from bottom to top. The first y that I see is -2. The last y that I see is 4. So the range is going to be -2 to 4. I don't include numbers that are interior to the domain. I only include two numbers in each, the domain and the range, which is the first and the last number. And the middle numbers don't get included. So the first four problems, 32, 33, 34, and 35, although they're infinite, have infinitely many points, they have a fixed starting point and a fixed stopping point. And those graphs, it's a little bit easier to find the domain and range of than the next problems. The problems 36 through 45, there's a point that's labeled, and the edges of the graph aren't labeled. For you, I think it's still the point 2, 1. These are hard to read. So because these points, this point is labeled, I'm probably going to have to incorporate it somehow in my answer. But the edges don't have periods. Like in problem 35, the edges of the graph had periods, which means the graph is stopped right there. In problems 36, 37, and in most of the rest of the problems, the graphs don't have periods at the end. That means I intended the graph to keep going up in the direction that it's going forever. But of course, you have to stop a graph. So if the endpoints aren't marked with a period, then you have to extend the graph. So I'm going to extend this graph, and when I go to do the domains and ranges of problems 36 and 37, I'll do 36, you'll do 37. It's going to be a little bit trickier, and my domain and my ranges are going to start to have infinities. So the graph for problem 36, it looked something like this, but the points at the ends weren't marked. And when the points and the ends aren't marked, you have to extend the graph before defining the domain and the range. So I'm going to extend this graph up and to the right and up and to the left. Well, now I'm going to try to put numbers on the x-axis to represent the edges of the graph. The first number I'm going to put on my x-axis is the number 2, which is the x-coordinate of that point. The next number I'm going to put on my x-axis is the x-coordinate of where this graph ends. And eventually, this graph goes up and to the right forever. It keeps going for right, and never stops going right. It ends, it doesn't really end. It gets to the far right edge of the x-axis, and the far right of the edge of the x-axis has positive infinity for its x-coordinate. On this side of the graph, it keeps going up and to the left forever, and eventually it tracks to the far left edge of the x-axis. So this graph eventually gets really high, and then if I looked up from the far left edge of the x-axis, I'd see it, and it gets really high, and if I looked from the far right edge of the x-axis, I would see it. So for my domain, I'm worried about numbers on the x-axis. I don't take middle numbers, I just take the first and the last number. The domain is going to go from negative to positive infinity. And this is where this kind of bracket that I put in is important. If a point is physically on the graph, when I put that number in the domain or the range, I get a square bracket. Infinities aren't actually points on the graph. Points that aren't physically on the graph get round brackets. And I'm going to put round brackets. Beginning of my domain is going to be at x equal negative infinity. The end of my domain is going to be at x equal positive infinity. Done with the domain, moving on to the range. I'm going to take the y-coordinate of this point, pop it on the y-axis, and when I extend the graph, this side of the graph makes it to the top of the y-axis, which has a y-coordinate of infinity. This side of the graph makes it to the top of the y-axis, which has a y-coordinate of infinity. So I just needed to extend it in terms of the y direction only to the top of the y-axis. It doesn't ever go to the bottom of the y-axis, so I'm not putting in negative infinity, which is down here on the y-axis, when I go to find my range. I took the y-coordinate of that point and the y-coordinate of where those were going, which is at the top of the graph when I go to do my range. And for my range, I look at the numbers on my y-axis. I only have two numbers on my y-axis. I have 1 and infinity, and I always read from bottom to top. The point 1 that starts off my range, because it comes from a point on the graph, gets a square bracket. The infinity, because it's not technically a point on the graph, when I put it into my range, gets a round bracket. So you should be able to do something similar for problem 37. It's a little bit different because it's upside down. Hopefully you can stumble through that a little bit. When I do problem 40, I have a graph that will have a similar range to your problem 37. So I'm going to do 38, and I like doing this on different sheets of paper. So when I go to do 38, the only point that's marked is this point 20. That means this side of the graph doesn't need to be extended because it's where it needs to be. And its x-coordinate is 2. I'm going to write that number on the x-axis as I go to find the domain. This side of the graph doesn't have a period, which means it needs to extend that way. And in terms of the x, if I'm trying to find the domain, it goes to the far left edge of the x-axis, which is at x equal negative infinity. I can see my domain. My domain's going to go from x equal negative infinity, and it's going to stop at x equal to 2. So for problem 38, my domain is going to be x equal negative infinity to x equal to 2. Points that are on the graph get square brackets. Infinities always get round brackets. Now I'm going to attempt to find my range. The first thing I'm going to plot is this 0 right here, which is the y-coordinate of the point that's marked. And then this graph, it goes very slowly, but it goes down forever. Eventually, it's going to make its way to the bottom of the y-axis very slowly, but it'll get down there because it keeps going down forever and ever and ever. And eventually, it'll get down to the bottom of the y-axis, which is the y-coordinate of negative infinity. So that's the other point that I need to mark for this. I don't need to mark anything up here because the graph doesn't. It terminates right at that period. For the range, I read from bottom to top, and the numbers I need for my range are negative infinity and 0. And I always go bottom to top for the range, left to right for the domain. So for the range for number 38, it starts at negative infinity and it ends at 0. This 0 came from the point 20 that was physically on the graph, so it gets a square bracket. Infinities always get round brackets. That should be similar to your problem 39, but they're a little bit different. Now I'm going to move on and do 40. Now, these points are so hard to read here. I think for both of ours, the point's 3, 1. When I go to do number 40, my graph looks like this, stops at the point, and goes like that, and it goes to the point 3, 1. When I go to do the domain, this side of the graph is going to extend forever. Eventually, it's going to get to the far left edge of the right x-axis. This graph's going to extend forever, and it's going to get to the far right edge of the x-axis, and the x-coordinate of that point is 3. When I go to do the domain, I read across, and I pick off my x values. The first x value I see is negative infinity. I'm going to ignore the 3 because it's interior, and then positive infinity. So the domain that I'm going to write for problem 40 would be negative infinity to positive infinity. When I go to do the range of problem 40, the number I'm going to put on the y-axis is 1, the y-coordinate of that point. And both of these sides eventually make it down to the bottom of the y-axis, which has a y-coordinate of negative infinity. So the other number I'm putting on the y-axis is negative infinity, which is the y-coordinate of the bottom of the y-axis. Now I can do my range. I read from bottom to top, and the range is going to go from negative infinity to 1. So range is always y's. Domains are always, infinities always get round brackets. Domain is always x's. Range is always y's. Just had a hiccup. And in infinite relations, you show interval notation. Infinities always get round brackets. Points on the graph always get square brackets. When a graph is just a series of scattered points that aren't connected, then you don't use interval notation. All right, so hopefully you can do problems 39 and 41. The next few problems are kind of cruddy graphs because I can't see the numbers so well, but I'll make a stab at them. I'll try to draw them a little bit bigger, and they're graphs that were probably graphs of fractions at some point. They're broken up graphs, and when graphs are broken into chunks like they are in problem 42, the domain and the range is likely going to be broken up into chunks as well. 42 is a really wretched graph because it's supposed to be microscopically above or below the x-axis. When you look at your problem 43, there's a gap between the graph and the x-axis on the right-hand side. There's supposed to be a gap between your graph and the x-axis on the left-hand side, although we can't see it. Our graphs are going to be real similar. 1, 2, 3, 4, 5. Let me reproduce this graph in a more suitable fashion because this is really hard to get a domain in the range. And maybe I'll do 43 for you as well. So my graph for 42, what it's supposed to look like, more clearly than it actually does look like, is it has two halves. I'm going to draw a dashed vertical line through 5 on the x-axis just to indicate where the break is. The break of this graph is supposed to be at x equal 5, and there's a half of the graph that's supposed to look like this, and it's going to stay microscopically above the x-axis for that half, and this half right here is supposed to look like this. If I had a better window, maybe it would look like that. So when a graph is broken like this graph in problem 42, when I go to do the domain and the range, my domain is going to be broken and my range is going to be broken. My domain is going to show the domain of this half of the graph and that half of the graph. Notice that when I drew all these graphs for 42, 43, 44, and 45, I didn't label any points because there weren't any top or bottom points that I could find. When I go to do the domain of this graph, I'm going to do the left half and then the right half. And I'm going to separate those domains. For this domain, for this part right here, this part of the graph tracks all the way out to negative infinity, and it goes and it stops at x equal to 5 right here. For this half of the graph, I'm going to say the domain goes from negative infinity to 5. Negative infinity always gets a round bracket because it's not a point on the graph. This x equal to 5, because the graph actually doesn't exist above and below this vertical line, the first half of the graph ends at x equal to 5, but there's no point with an x coordinate of 5, so I should put a round bracket. The second half of the graph, it ends, it goes off to the right, it goes to positive infinity, and the second half of the graph, it starts just to the right of x equal to 5, and it ends at infinity. And again, there's no point on the graph that has 5 as its x coordinate, so the second half of the graph, I'm going to say, goes from 5 to infinity. When you have a broken domain, when it's broken into two pieces, you usually put a U symbol, which kind of means union or between the pieces for the domain. When I look at this graph for the range, I'm going to look at each half again. This half right here, it goes down to the bottom of the y-axis. The bottom of the y-axis has a y-coordinate of 0. This half, it bottoms out just under the x-axis. The x-axis has a y-coordinate of 0. This part of the range is going to go from y equal negative infinity to the y-coordinate of the x-axis, which is 0. So the bottom half right here is going to have a range from negative infinity to 0. The top half right here, it bottoms out at the y-axis, which has a y-coordinate of 0, and it goes up to the top of the y-axis, which has a y-coordinate of infinity. It's going to have a range of 0 to infinity. I put the 0 in round brackets because as I look across the x-axis, which is y equal to 0, there's no point on the x-axis. There's no point that has a y-coordinate of 0. When there isn't a point on the graph that has that x or y-coordinate, you get round brackets. When you have distinct disjoint pieces that make up the range, you put unions between them. Let me make a better copy of problem 43 for you and walk you through the domain and the range. So 43, it's supposed to look like, that's at 2. At x equal to 2 is where its break is. And it has a left half that looks like this, and a right half that's supposed to look like this. And both of these graphs are supposed to be microscopically above or below the x-axis. So I'm going to go and pop out the domain for this for you. The number that belongs on my x-axis is 2. That's where the x-coordinate of where the break is. For this half of the graph makes its way to x equal negative infinity. So I'm going to read from x equal negative infinity to x equal 2. This is the first part of my domain. And because there's no point on the graph that has 2 as its x-coordinate, I'm going to say the domain goes for this half from negative infinity to 2. This half of the graph, the right edge goes out to positive infinity. And I'm going to say the domain of this half goes from x equal to 2 to x equal infinity. And I'm not going to put the 2 in a square bracket because there's no point on the graph that has 2 as its x-coordinate, so it's going to be in a round bracket. And I'll put a union symbol between. For the range, I'm worried about this half than that half. For this half right here, it goes down to the bottom of the y-axis, which has a y-coordinate of 0, and then it goes up to the y-axis, and the y-axis has a y-coordinate of 0. So this piece right here is going to have a range of negative infinity to 0. There's no point that has 0 as its y-coordinate, so it gets a round bracket. This piece right here stays just above y equal to 0, which is just above the x-axis, and it goes to the top of the y-axis, which has a y-coordinate of infinity. Its end of its range is going to go from 0 to infinity. I think I'm just going to steal your problem 45 and get that done for you, and I'll do 44. Year 45, it has a break at x equal negative 1 vertically. And I can't see the break so well there. Let me blow up. Maybe I get my reading glasses and can actually read this better. Sorry for the microly small numbers on the axes. I don't know if they're incremented by ones or not. So I can't read it. The fact that I can't read it, I guess this is going by ones. So this is 1. This is 2. This is a wretchedly bad problem because it's not. Well, let me draw a picture of 45 how I intended it to be. It's not the best problem that I could have ever written. So 45 looks like it has 2 halves. The left half looks something like this. And the right half looks something like this. This problem, it's not so bad to get the domain, but it's really tough to pick out the range, especially when I draw this. I kind of made it up too high, I guess, but oh well. Let me do the domain first. This left half right here, it goes out to the far left edge of the x-axis. It makes it to this break point, which is x equal negative 1. So my domain is going to go from x equal to negative infinity to x equal to negative 1. Round bracket because there's no point that has an x-coordinate of negative 1. This half of the graph starts at x equal negative 1, just to the right of that, goes out to the far left edge, right edge of the x-axis, which has an x-coordinate of infinity. So that's going to have a domain of negative 1 to infinity. Put a union symbol between. For the range, this half of the graph has a top of y equal to infinity. And boy, I'm not convinced that what the bottom, where that break is going this way, but there is a break here. And it's not a slanted line like that. And my very best guess is the break that this graph has is at y equal 1.5. It's not 100% conclusive, but that certainly looks like there's a break. This break right here occurs at y equal 1.5. So for this part of the graph, it stays above y equals to 1.5 and it goes up to y equal to infinity. So for the range, I'm going to say this part goes from 1.5 to infinity. This part of the graph goes down to the bottom of the y-axis, which has a y-coordinate of negative infinity. I'm going to say it goes from y equal to negative infinity up to y equal 1.5. Really unfortunate on multiple fronts. The numbers on the axes are too small, and I shouldn't have a decimal for the y part of the range because it's just too hard to estimate. But that's my best guess at what this should be. If I snuck something like this on a test, the graph would be much bigger like this, so it's going to be obvious where the breaks are in terms of the x breaks are usually easy to see. If the y break isn't at the x-axis for y equal to 0, a lot of times it's hard to see. So, there's still 20 more problems in this section. Got 40 minutes into this video. I think this is a good place to stop. I'm going to do a part 3 to this. There's going to be a couple of really long sections in chapter 3, and unfortunately that's just what college algebra is. There's a lot to cover. So I'm going to stop the video and do a part 3.